This video is going to be an introduction to SIR models for the spread of disease, which probably a lot of people are making videos about right now, but here's mine. So we've all probably been seeing graphs that look like this, and when we hear about flatten the curve, this is the curve we're talking about here, this guy. What we're looking at is the susceptible people in a population over time, which is falling. We have the number of people who recover, which fortunately goes up over time, and the thing we want to flatten is the number of people who are infected at any given time, which is represented by this green curve, and we have a peak here, which we'd like to be smaller. So how does this model work? Where are these graphs coming from? What is the history behind this? Well, what we're looking at here is the simplest SIR model, the first one, which was developed by Kermack and McKendrick in Scotland in 1927. They have a paper called A Contribution to the Mathematical Theory of Epidemics. I'll put a link in the description if you want to look at the original paper. So how does this model work? It assumes that we can divide our population into three parts: the susceptible, the infected, and the recovered. So S, this bucket, represents people who are at risk of getting the illness. I is the fraction of people that are infected, and R is the fraction of the population that's recovered. So what are the assumptions beyond this in this model? It's always important to list what your assumptions are in a model. We're going to assume that there are no births for what we're doing here, so the population size stays fixed. We're not adding to the S bin. There's also no immigration. We don't have population growth by any means. Recovery gives total immunity. So once you recover from whatever this illness is, you no longer are susceptible to this. This depends on how much a virus mutates, some other factors, but we're going to assume for simplicity that once you recover, you can't get it again. There's a fixed infection rate per day. So how many people does an infected person come into contact with per day? And there's a fixed recovery time. Maybe it takes 2 weeks to recover from this illness that we're modeling. And people are well mixed. So this is maybe a more esoteric assumption, but assume people behave similarly throughout the region that's affected, so we can actually characterize number of contacts per day and the amount of time to recover. These things are uniform throughout the region that's affected. So one way that you can imagine these bins being related is imagine that the S bin is full of some liquid, maybe some paint, and it is mounted above the I bin. But not only mounted above, also tied to the I bin, so that when the I bin gets some paint spilled into it, the I bin becomes heavier, and that pulls on this string, which tips the S bin further. So the heavier the I bin is, the faster the S bin will empty. But also, the S bin's emptying depends on how much is already in the S bin. So it depends on both how much paint has spilled already and how much paint is left to spill. So how could we model that with an equation? The rate of change of S versus time, that's what this derivative notation means. The change in S over the change in time is going to be a decrease. We're getting fewer susceptible people as they become infected. That depends both on how many people are available to become infected and how many people are already infected. So this paint bucket model is a nice metaphor. I like the physical demonstration there. What are the units of this beta constant? Well, that is the number of contacts per infected person per day. Let's take a look at how that works. So suppose I'm an infected person, I go about my day and I come into contact with people, and the number of contacts per day for me is 3, so these 3 random people also become infected. Why does it matter how many people are in the red population, the susceptible population? Well, let's see. Let's suppose that these individuals over here are already immune, maybe because of a vaccine, or maybe because of genetics, or maybe because they've already had the illness and recovered. So why would that mean that I infect fewer people? I infected those 3 random people. We can compare with before that one of those people who used to get infected doesn't get infected anymore because they're in the protected population here. So these 2 would still get sick, but this person is protected. So that is why the rate of infection, the rate at which we deplete the susceptible population, is proportional to the number of people who are already in the susceptible population. It's probably more obvious why the rate at which we deplete healthy individuals, susceptible individuals, is proportional to the infected people. Let's see what happens if we have more infected people. They each have a contact of 3. It might luck out that some of them contacted the same people only, but if they each contacted 3 different people, now we've got 9 of our original 10 infected. So this is a pretty good story for how we deplete the susceptible population. It depends both on S and I. But how do we know how quickly we're filling up the infected bucket? Well, this bucket's loss, the red bucket's loss, is the green bucket's gain. So I know however quickly I'm pouring out of the top bucket, that's how quickly I'm filling up the middle bucket. So the middle bucket's rate of change is not negative, but positive because it's filling up, and it is just the same amount. Now, things would be unfortunate if this was the end of the story, but a fortunate thing about most illnesses is that you recover from them. So we drill a hole in the middle bucket, and it can drain out. Now the rate of change has both additions and subtractions in this bucket. So we add another term to our equation, beta Si minus gamma I. Remember, beta was the number of contacts per infected person per day, and gamma is going to be 1 over the amount of time it takes to recover. So this is the rate of recovery. If the illness takes 20 days to recover, then gamma would be 1/20th. So we're filling up the bottom bucket. How quickly are we filling it up? Well, I know that any gain in this bucket is from the middle bucket's loss, so my rate of change of the recovered population has to be just the opposite of the rate at which I drain the infected bucket. So dr dt, the rate of change of r with respect to time, rate of change of recovered people with respect to time, is just the rate at which we fill this bucket, which could depend on how big this hole is, or maybe how good your medical treatment is, or maybe how healthy you were before you were infected. So this is our model. We have the 3 equations, and let's see how they relate to these 2 constants. Remember, beta was the contacts per infected person per day. Gamma was the recoveries per person per day. You could figure that way if it took 20 days to recover, you could imagine that you were recovering a 20th of the way each day of that time period. So if that's recoveries per person per day, then 1 over this number will be the days to recover. Now, if we assume that you're moving about still when you're infectious, when you're contagious, then the number of contacts per day times the days to recover would be the number of contacts you have while you're infectious. So we can take that ratio, beta over gamma, or beta times 1 over gamma, and that's the contacts per infection. This is the most important number, a lot of people would argue, in epidemiology, that we call R0 or R0. If this number, the ratio of beta and gamma in our model, is greater than 1, then the infection is going to spread through a population. And if it's less than 1, then it won't. It'll spread some, but it won't have exponential growth. It'll decrease and die out over time. So the really important thing for us behavior-wise is to get this number as close to 1 as we can, and ideally less than 1. But there's a difference between the numerator and the denominator here. People can't do a whole lot to change the amount of time it takes to recover from an infection, but we can do a whole lot to change the number of contacts we have per day, and that's why social distancing is so important, because there's not a lot you can do about the denominator, but there's a lot you can do, painful as it might be. You can change your behavior and reduce the contacts per day, which it's best to just assume that you're already infected, and that will lead to the behaviors that make the most sense. In a future video, we're going to see how do you actually solve these equations. But let's look at how they relate to the graph just for a quick introduction. We see that the rate of change of S is always negative. These numbers are never negative numbers themselves, and beta is a positive constant. So with this negative sign here, I see that susceptible is always decreasing. Similarly, R is always increasing. But the green population, because it has 2 terms, one that's positive and one that's negative, we get this kind of growth followed by a peak and a decay. So The story told by these equations matches what happens when we solve the equations, but solving them involves a few tricks, as differential equations always do, and that is a story for a future video.